Hi, my name is Hikari Bayashi, and I'm gonna talk about minimum sharpness, scale-invariant parameter robustness of neural networks. Let me start with the background. Robustness of neural networks. When we refer to the robustness of neural network, we usually mean the input data robustness. In other words, the robustness against adversarial examples in data. This type of robustness has been an active research area since the pioneering work by Goodfellow et al. 2014. Also, the second type is the robustness of weight parameters, or often called sharpness. Compared to the first one, the second type of robustness hasn't attracted much attention, but there are works showing that it has close relation with the model performance. However, how to formulate sharpness is still controversial because of its scale sensitivity. Naively defined sharpness is known to have nuisance sensitivity to a specific transformation called alpha scale transformation. Then, what is alpha scale transformation? Consider a neural network which has D layers with weight parameter W and activation function phi. Here we focus on activation functions with non-negative homogeneous property, such as ReLU function. Alpha scale transformation is a layer-wise transformations by a collection of scalar values, alpha 1 to alpha d, and whose total product is 1. This transformation does not change the functionality of the provided neural network at all, but it changes the value of sharpness. For example, suppose h of theta represent the Hessian matrix at theta. Although the trace of Hessian is one of the typical definitions of sharpness, it changes under alpha scale transformation. This implies such a naively defined sharpness does not reflect the property of models, and calling for the necessity of scale-invariant sharpness. Here's our proposal. To circumvent the scale sensitivity, we propose minimum sharpness that is defined as the minimum of Hessian trace under all possible alpha scale transformations, which is formally defined like this. By its definition, minimum sharpness is invariant under alpha scale transformations. Here, as you notice, minimum sharpness include Hessian on parameter space, which is notorious for heavy computation, and also include unknown minimization problem over alpha. So how do we compute those? Here's our approach. Hessian computation is heavy because it involves the second order derivative. In this paper, we found out that Hessian trace can be reduced to the sum of the first order derivatives, which is efficiently computable. More specifically, this is the informal version of our proposition in the paper. And here, let me note that the h theta d means the Hessian trace at layer d because Hessian trace can be defined layer-wise. And thanks to the proposition 1, the original minimization problem is reduced to a simple d-dimensional optimization problem, where d is just a number of layers. Therefore, minimum sharpness can be efficiently computable. Even further, we prove that the minimum sharpness takes closed form when the architecture is no bias, fully connected neural network. Specifically, this is the actual closed form. Now, in order to validate our minimum sharpness, we conducted several numerical experiments. Our first experiment is about efficiency and the accuracy compared with the ground truth. Here, the ground truth is the naive computation of the second-order derivatives. We used a fully connected neural network and a convolutional neural network as an example. Here, as you can see from the left figure, our results are quite aligned with the ground truth. Also, as shown in the right table, our method is much faster than the naive method. Also, to verify the minimum sharpness is a valid sharpness measure, we conducted a randomized label experiment where we trained fully connected neural networks with MNIST with partially randomized labels. Here we confirm that our minimum sharpness correlate with the generalization gap, which implies minimum sharpness properly quantifies the performance of model. In summary, we proposed minimum sharpness that is a novel scale-invariant sharpness measure. We also developed a method to efficiently compute minimum sharpness, including the efficient computation scheme of Hessian trace. Finally, we conducted a numerical experiment to verify its efficiency, accuracy, and validity. Here, all the related codes are available on this link. Thank you.